In this screencast, we're going to do an Exam 4 review on Alkenes and Alkynes for the Spring 2018 Organic Chemistry 1 semester. Problem 1 is asking us to determine the name given the structure of the compound. And so let's go ahead, figure out what the major functional groups are present in this molecule, and then from there determine which one's going to be the parent, and then count the longest carbon chain. So the major functional groups, we have an alcohol, we have an alkene. So the alcohol is the higher oxidation state, so that's going to take preference in terms of the parent functional group. And it also has to have the lowest locant number. So therefore we're going to start the chain numbering here at this methyl. That's 1. The alcohol is going to be at carbon 2. So when we scan down our choices, we can eliminate B because that's showing the alcohol at 6. Let's go ahead and count the rest of the carbons. 3, 4, 5, 6, 7. So we're dealing with a heptane derivative. So therefore we can go ahead and eliminate A. And now we have to determine between C and D. We see that there's a methyl group at position 5. So the compound is going to be 5-methyl 4-heptene 2-ol. And what we have to determine is the geometry, whether it's E or Z. And in this case, if you look at both sp2 hybridized carbons of the alkene, which I've highlighted in blue, and you prioritize the groups on each of those, on the right-hand carbon is going to get priority 1 over here. On the left-hand carbon, this gets priority 1, so they're on the same face, so that's going to be the Z or cis. So E means trans, as a review. Problem 2 is asking you which of the following molecules is the strongest base. And so what you really need to do is draw the conjugate acid of each of these. So for butyllithium, the conjugate acid is butane, and then have a rough idea of what the pKa values are. So for an alkane, that's going to be 50. Sodium hydroxide, the conjugate acid is water, that's going to be 16. Sodium methoxide, another alcohol similar to water, just kind of keep it the same at 16. Sodium amide, the conjugate acid is ammonia, and that's going to have a pK of about 38. So the strongest base is going to be the weakest acid, so that's going to be the alkane, so this answer is A. Question 3 is asking you which of the following is the strongest acid. So again, that's the ability to donate a proton, and then just draw these out. Propane is an alkane, the pKa of that is 50. 1-butyne. So this is a terminal alkyne. We have an sp hybridized carbon. That hydrogen has a pKa of about 25. We have 2-pentyne. So now this is an internal alkyne. So all the hydrogens in there are going to look like alkanes, so they're going to be about pKa of 50. And then 3-hexene. So you have sp2 hybridized CH bonds that are a little bit more acidic than sp3 hybridized carbons, so these have a pKa of about 35. So in this case, the strongest acid is going to be B1-butyne. In question 4, you're given 2-bromo 2-methylbutane, and it's treated with different bases as shown here. And it's giving you a product distribution, and they're specifically saying, they're asking you how the ratio of the 2-methyl-1-butene is going to change. And so if you look, this is a tri-substituted, this is a di-substituted alkene. So this is the Hofmann alkene, and then this is the Zaitsev alkene. And what this question is asking you is you're starting with KOH, which is a small base. You're then going to potassium terbutoxide, which is a large base. And you see this ratio grows. So what if you use a base that's in between, and we say medium-sized base? You're going to get a ratio that's between 45 and 70%. So the answer for this one is going to be C. Question 5 is asking you which of the following alkenes is the most stable. And again, you want to draw them out and then rank them. So 1-pentene. So this is a monosubstituted alkene. Then you have E,2,3-dimethyl 2-pentene. So E is the trans. So this is tetrasubstituted. Cyclohexene. That's disubstituted. And then 1-methylcyclohexene. This is tri. So the tetra is the most stable, and again, that's determined from the heat of hydrogenation, so this answer is B. Question 6 is asking you to rank the following carbocations in order of decreasing stability. So 1 is the most stable, and what you need to do is just identify or classify what type of carbocation they are. 1 is a phenyl. That carbocation, the plus charge resides in an sp2 hybridized orbital, so that's pretty unstable. So that needs to be ranked the lowest. So if you look at your choices, A and C are out. Then the remaining ones, you have secondary, but this is benzylic, so that's special. And then you have primary. So 3 should be ranked number 1. So if you look at your choices, you can eliminate B, and so the answer for 6 is D. For question 7, you're given a reaction coordinate diagram. So along the x-axis, you can think of that as time or bonds being made and broken, and the y-axis is energy. So we're starting, draw this line here, and the peak at this point is a transition state, and I'm going to call that transition state 1. You have another peak, that's going to be transition state 2, and then in this well here is an intermediate. So the energy of activation, you have to compare the energy to get to both transition states from this flat line that you're starting here from your starting materials. So you can see that this is greater. So transition state 1 energy is greater than transition state 2. And overall, you have to put energy into this reaction. So that means it's an endergonic reaction. You have to put energy in. It's 2 steps because you see 2 transition states, and the first step is the rate determining because you have to put more energy to get over it. So the answer for this one is C. Question 8 is asking you about an E2 reaction. So bimolecular elimination. You're forming an alkene. So to do that, you identify the carbon bearing the leaving group. So in this case, the leaving group is the tosylate. That's the alpha carbon. You go out to both beta carbons, so beta and beta. And so in this case, you're treating with potassium terbutoxide. So that is a large base. Potassium tertiary butoxide. That's going to favor the Hofmann elimination. And what that means, of the beta carbons bearing the most hydrogens, that's the one that's going to be abstracted. So in this case, it's going to be HA. That gives you the least substituted alkene. So the product for this ends up being 1-butene. Question 9, you have a diene, so that's 2 alkenes you're treating with excess ozone gas, followed by a reductive workup. So ozone gas, remember this is going to do an oxidative cleavage. So each alkene gets cleaved. Let's go ahead and draw in this substituent here. So when you look at that alkene, this carbon forms an aldehyde. This carbon forms a ketone, as does the remaining 2 of this other alkene. So you need to have aldehyde, ketone, ketone, ketone. So the correct answer for this one is going to be C, which is the one that shows you the ketone being split off. So propanone plus the ring opening. A is not correct as they did not cleave that as well. Question 10 is asking you about a tri-substituted alkene being treated with bromine and water. So bromine is your electrophile, and water is a participating solvent. So remember what that means, in that water is going to be incorporated into the product. And the way that the bromine acts as an electrophile, you form a bromonium ion, and it's trapped by the water in an anti-fashion. So in this case, the bromine and the water have to be on opposite faces. So if you look, really you can eliminate B and D as they're showing the syn addition, and we need anti. The correct answer for this one is going to be 10. And the reason for that is when the water attacks, it's going to attack the more substituted carbon of the bromonium ion, because that carbon has more of the positive charge of the bromonium ion. Question 11 is a bromination. So we're going to form a 1,2-dibromide. And there's no solvent given, so this is non-participating, meaning that solvent is not incorporated into the final product. So in this alkene, we're starting with cis-2-butene. We're going to do an anti-addition of bromine. And then we basically have to look at these Newman projections to figure out which one of those gives the anti-addition of bromine. So as you scan these Newman projections, again, you're looking down that bond when the addition happens. So B is a derailer answer because the front carbon has 2 hydrogens, and it basically should have 1 hydrogen and 1 methyl group. So that leaves you A, C, and D. A and D are actually rotational conformers of one another. So they're actually the same compound. So you can't choose either one of them because they're essentially the same answer. So the answer for this one ends up being C. And so how do we figure that out? When these bromines look like they're syn to one another, the problem actually has done a rotation, and that's what you have to realize. So let's go ahead and look at a mechanistic proposal for this. So in a bromination, The alkene is a nucleophile attacking the electrophile. A lone pair comes back up, we form the bromonium ion, and then we cleave this sigma bond. So let's go ahead and draw the bromonium ion. So plus. We then have bromide that's going to attack in an anti-fashion. So let's go ahead and just draw that anti-relationship now. There's our 180-degree dihedral angle. We fill in our remaining substituents. And at this point, you're doing a Newman projection looking down that C2-C3 bond. And so what you'll find is that C is the correct answer after you've done a rotation. Problem 12 is asking you about the major product from a hydrogenation reaction. So H2 gas, transition metal, and protic solvent. Is hydrogenation of an alkene, so you're removing a degree of unsaturation. So this is a syn addition. Across the alkene. So both hydrogens have to end up on the same face. So if you scan these answers, you can eliminate B. That's showing an anti-addition. So the hydrogens are on different faces. C can be eliminated because both hydrogens end up on the same carbon. A is eliminated because they have not reduced the alkene. So the correct answer is D. You have the syn addition of hydrogen. In question 13, you're asked what the product is when R, 3-methyl-1-pentene, is treated with HBr. So you need to go ahead and draw out that structure. So here we have the 1-pentene. Now we need to draw in the 3-methyl with the R stereochemistry. So if we do that, we're going to go ahead and put the methyl group back. So how did we determine that? So here's the stereogenic carbon with the blue asterisks. We have priority group 1, 2, 3. We're going counterclockwise, but the lowest priority is towards us, so we reverse it to get clockwise, so that gives us the R. So when we treat an alkene with a strong acid, we have a choice to protonate either carbon of the alkene. So I'll call this carbon 1 and this carbon 2. So let's go ahead and draw both those choices if you protonate each of those. So we'll protonate 1. That generates a carbocation here. That's a secondary carbocation. If you protonate 2, that generates a primary carbocation. So this, if you compare, protonation of 1 is preferred, 2 is not. So anytime that you form a carbocation. Let's call that our alpha carbon. You have to look to the neighbors. You have a beta and a beta carbon to see if a rearrangement can occur. So in this case, a rearrangement can occur. We call that a 1,2 hydride shift, in which this hydride moves over. That's going to generate a tertiary carbocation in this case. So here's our remaining methyl group. And at this point, this intermediate is achiral. Bromide can then attack from either face of the p orbital, and you generate a racemic 3-bromo-3-methylpentane. So the answer for this one is A. B, C, and D are not correct because as you proceed through this mechanism, you destroy the chirality that you're starting with. And so let's go ahead and question 14 is asking you to identify the nucleophile that attacks a carbocation intermediate in an acid-catalyzed hydration of an alkene. So you're in neutral medium and you need a nucleophile. So in acid, this is an electrophile. This is an electrophile. And you can't have hydroxide in acidic medium, so this is a base. So the correct answer for this one is D, water. So what do we mean by that? So say you're looking at propene, you're treating it with hydronium, you form the most stable carbocation. Water is then the nucleophile that attacks the carbocation, and you end up with your alcohol. In problem 15, we're looking at acidic treatment of a secondary alcohol with heat. So anytime we have an alcohol in the presence of an acid, the alcohol acts as a base. So we're going to protonate that OH. So let's go ahead and do this mechanism. So we have a 5-membered ring, we have a 4-membered ring. We've protonated the OH through an acid-base reaction. We then ionize. So this is the slow step. We form a secondary carbocation. We have a beta carbon that's in a 4-membered ring. So what happens is a migration. So in this case, we're going to do a ring expansion. Let's go ahead and number that so we can see it. So we're starting at the carbocation 1, 2, 3, 4, 5. So now we're forming a bond between carbons 1 and 5. So we're generating a 5-membered ring. Let's go ahead and put those numbers back in so we can see what happened. 1, 2, 3, 4, 5. Carbon 2 is now bearing the plus charge. Carbon 1 still has a proton. That's eliminated. And so the answer for this one ends up being C. So you end up with a 5-5 ring system. Question 16 is asking you about degrees of unsaturation for the terpene caryophyllene. So if you're hydrogenating it with palladium metal in hydrogen gas, you're going from C15H24 to C15H28. So just by visual inspection, you can see that you're adding two equivalents of molecular hydrogen through this process. So that's telling you that 2 degrees of unsaturation are being removed, which is equivalent to 2 pi bonds. But then it's also asking you how many rings are in this molecule. So let's use the equation CnH2n plus 2. So we have 15 C15H32. Let's go ahead and subtract C15H24. That gets us H8. We divide by H2, so that gets us 4 total degrees of unsaturation. And you can see through the reaction that 2 degrees of unsaturation were removed through hydrogenation, so that leaves us 2 degrees left, so that's going to be 2 rings. So the answer for 16 is D. 17 is asking about the general mechanism of electrophilic addition to an alkene. So the answer for this one is A. The arrow always originates from a nucleophile. So if we do a very general example of this, so the pi bond is the nucleophile, it's pointing towards the electrophile. And the arrow is representing the movement of a pair of electrons. So the 2 electrons on the pi bond are forming a new bond to that hydrogen. So the correct answer for this is 1, 2, and 3, which is A. In 18, it's asking you which of the following alkene addition reactions occurs specifically in the anti-fashion. So remember, there's syn versus anti. So hydroboration is a syn addition. Bromination is anti. Hydrogenation is syn. The addition of water gives you a mixture of both, depending on the substrate you start with. So the correct answer for 18 is B. '19 is asking you about the functional groups present in Taxol. So just go through and list them. You have an alcohol. So you can eliminate C, that shows no alcohol. You have an ester. You have an ether. You have an amide. So if you scroll through, you'll see you have no nitrile present, so A is out. You have a ketone as well. So because A is out, D has nitrile as well, that's out, so the correct answer for this one is B. So for questions 20 to 25, you're asked to use the reagent table that was provided at the end of the exam. And specifically for question 20, what reaction sequence is going to produce cis 2-pentene from acetylene? So again, the best strategy is to draw these things out. What sequence produces cis 2-pentene? So look at your starting reagents. So reagent 19, if you look at A here, that's H2 gas, and if you started with that, you would reduce the acetylene down completely, so you don't want to start with that. The other three start with 8, which is sodium amide. And they're all basically proceeding through these same first couple steps. So you really can't eliminate anything here until the end. So step 1 is doing a deprotonation. Then you're treating with reagent 10, which is methyl iodide. So you're installing the methyl group. Then you're treating with sodium amide again. Then reagent 16, which is ethyl iodide. So you're getting all the carbons in the chain. So you're getting to this point. And then at this point you need to treat this alkyne to form a cis alkene. So reagent 7 is reagent 7 was hydrogen gas and palladium. That's going to do a full reduction, so you want to eliminate B. 11 was sodium metal. That's going to give you the trans alkene through a dissolving metal reduction. So the correct answer for this is D, which is going to do the Lindlar reduction in the final step. 21, you're taking a tertiary alcohol and you're making a primary alcohol. So if you think about how you make a least substituted alcohol, so that can come through a hydroboration oxidation of this alkene. And how do you take an alcohol to an alkene? This is a dehydration of an alcohol. So look at your reagents. So in A, C, and D, what you're doing in the first step is activating the alcohol. And you specifically want to form the least substituted alkene. Of the potential possibilities here. And so at this point, if you look, you might think that B is a reasonable choice given that that reagent is sulfuric acid. But what is going to happen if you treat that starting alcohol with sulfuric acid? It's going to dehydrate to that, and the alkene is in the wrong place. So at this point, you can eliminate B. So A, C, and D are converting the alcohol into a good leaving group. So that's chapter 6 reactions there, conversion of an alcohol into a good leaving group. Now you need to do an elimination, specifically a Hofmann elimination. So if you look at the choice between 15 and 6, you have potassium tert butoxide and sodium hydroxide. You're going to want to use the potassium tert butoxide, which is reagent 15, so you can eliminate C. And then finally, you look at what 14 and 18 are. So 14 is hydroboration oxidation, and then 18 is sulfuric acid again, which we saw in B here. So we can eliminate that, and the correct answer for this one is A. So moving to 22, you can see that we're starting with a terminal alkyne. And if you just count the number of carbons in the final product here, you have 1, 2, 3, 4, 5. So basically you have to do an acid-base reaction, then an SN2 reaction to get you the total number of carbons in that chain. So again, you're going to want to treat with a strong base and then ethyl iodide. So if you look at these choices, 6 is sodium hydroxide, so B is out. 15 is potassium tert-butoxide, so that's out. You really want a strong base, so now you're between A and C. Then you need to find the correct electrophile. A is out because 10 is methyl iodide. And so if you look at reagent 16, that's the ethyl iodide. So these 2 steps here are correct. That's going to get you into the manifold of getting the right number of carbons in the chain. Then reagent 11 is reduction to the trans alkene, and then the final reagent 9 is the dihydroxylation reaction. So the correct answer for this one is C. So in 23, you're taking an alkene and you're doing a substitution at the more substituted carbon of the alkene. So you need to convert to an alcohol or some other leaving group, and then do a displacement with sodium, lithium, or potassium cyanide. So let's just go ahead and look at each of these reagents. So if we look at A, reagent 18 is sulfuric acid. So the first product of this is going to be that. Then reagent 17 is sodium cyanide. This isn't going to work because OH is a bad leaving group. So A is out. What about B, reagent 4? You're treating with HBr. So at this point, the product of that is going to be the product of step 1. Then you're treating with reagent 17 with the sodium cyanide. So that's actually going to be the right answer. You're displacing that secondary bromide with cyanide. Reagent 3 is not correct because that's bromine. So the product of that is going to be bromine and bromine. And then if you take that product and you treat with reagent 13, they're not compatible reagents. And then finally, if you look at D, reagent 14, you're going to do hydroboration, and so that's not going to get you the product alcohol of that will be this. So you're functionalizing the wrong carbon of the alkene. So 24 is a road map problem in which you're given an unknown compound Z that has a molecular formula C6H6. You're treating that with reagent 19. That's a Lindlar reduction. So what does that do? That takes an alkyne to a cis alkene. So that's giving you Z is going to compound Y. And then when that compound is treated with reagent 1, which was potassium permanganate, sodium hydroxide, and heat, remember that's going to do oxidative cleavage. That gets you compound I. Or excuse me, that gets you compound 1,4-butane dioic acid. So what does that look like? Just go ahead and draw it out. And 2 equivalents of formic acid. So this is important as well. The fact that you're forming formic acid, 2 equivalents, means that you have to have a proton on the alkene that you're forming from the Lindlar reduction. It also says treatment of Z with reagent 7 gives you hexane. So that's a full reduction of the unsaturations in the molecule. So what's one thing you can do? You definitely have to have 6 carbons in the molecule. So go through and just count each carbon. So 1, 2, 3, 4, 5. So A is out. 1, 2, 3, 4, 5, 6. This could be a possibility, but it's an internal alkyne, and you have to have basically terminal alkynes to get the products that are listed in the roadmap. So if you do counts here, this is a possibility. D is a possibility based on carbon count as well, but again, you can eliminate it the same way you can eliminate B, in that you have these internal alkynes. You need these terminal protons to end up forming the formic acid from the potassium permanganate reductive oxidative cleavage. So the correct answer for 24 is C. An unknown alkene gives propanal as the only product upon treatment with 5, and that's ozonolysis. Remember, that's oxidative cleavage. So if you look at your choices, it's saying only propanal. So what is propanal? It's the C3-aldehyde. If you look at your choices, if you cleave A, you would get propanal, plus you would also get this aldehyde. So A is out. If A is out, C is out, because they're just geometrical isomers of one another. This is the cis, this is the trans. So your choices are between B and D. And it says when the unknown is treated with 3, so 3 is molecular bromine and carbon tetrachloride, so that's a non-participating solvent. You're forming an optically inactive dibromide that cannot be resolved into enantiomers. So remember that a vicinal dibromide occurs in an anti-fashion, and if you're forming in an anti-fashion something that's optically inactive, that means you're forming a meso compound. And when you do that, you'll find that answer B is the one that's going to give you the meso. So how do we determine that? So the transalkene forms the bromonium ion. So it's important to draw this stereochemistry in so that you can see how this anti-addition takes place. At this point, bromide will attack. So let's draw that in the anti. Keep your stereochemistry in. And what you need to recognize now is that if you do a rotation about that sigma bond, that the bromines will mirror one another, the ethyl groups will mirror one another, and the hydrogens will mirror one another. So in this case, you have an internal mirror plane, and that's a meso compound. So again, the correct answer for this one is B. If you go through with the same type of analysis with D, you'll find that you do form the enantiomers. So again, this has been an exam 4 screencast review on alkenes and alkynes.